Okay, next up we are going to sketch the graph of one of our rational functions. I like to go through 3 steps, ask myself 3 questions when I'm graphing one of these. First up, does this rational function have any holes? Holes happen when you have a factor common to the top and the bottom. This doesn't have any factors, nothing can be reduced, so there are no holes. That doesn't have to be part of your answer. This is just the process I'm thinking through when I graph these. Next up, I want to know where are the intercepts. I like to start with the y-intercept because that's the easier one to find usually. We just plug in 0 for x. So we get 3 over 0 minus 4, which is negative 3/4. That means we have a y-intercept at the point x equals 0, y equals negative 3/4. X-intercepts sometimes take a little more solving, not so bad on this one. We set our rational function equal to 0. If we multiply both sides by x minus 4, 0 times x minus 4 is 0. And on the right-hand side, they cancel. 0 equals 3. Well, that's not true. That's a contradiction. So that tells us that there are no x-intercepts. Next up, I want to look at asymptotes. Okay, for asymptotes, I'm going to start with our vertical asymptotes. Vertical asymptotes happen where your denominator is equal to 0. So here we have a vertical asymptote at x equals 4. Then for our horizontal and oblique asymptotes, we evaluate those together. We look at the degree of our numerator compared to the degree of our denominator. The numerator of our rational function has no variable, so it is of degree 0. There's just a constant up there. The denominator has x just to the first power, so the degree is 1. Anytime the top is smaller than the bottom, we will have a horizontal asymptote at y equals 0. If we have a horizontal, we do not have an oblique. We have one or the other, not both. So then what I want to do next is sketch in what I have. Let's see where we are. Let's mark those asymptotes with some dashed lines. So we have a vertical asymptote at x equals 4. We have a horizontal asymptote at y equals 0. So these kind of behave as guidelines for the rest of our graph. And then we just have one point, just that one little lonely point. Our y-intercept is at 0, negative 3/4. So we definitely are going to need some more points to be able to graph this function. So I would make myself a little t-table. We want to pick values for x, but we want to pick smart values for x. We already have x equals 0 right here with our y-intercept. So maybe x equals 1 and x equals 3 would give us an idea of what's happening. This is another case where we could use that table button if we wanted to. We could put in our rational function 3 over x, x, there we go, minus 4. And I do want to leave it on ask again. And I want to plug in x equals 1. That tells me y is negative 1. And then I also want to plug in x equals 3. Oh, look at that. I had it already here. That's y equals negative 3. So with our intercept in those 2 points, that should give me a pretty good idea of how to sketch it out. Positive 1, negative 1 for our next point. Positive 3, negative 3 for the next point. We want to connect those with a nice smooth curve, and then we want to continue toward our asymptotes in both directions from there. Don't stop there. That's only half of our graph. We also need to see what's going on over here where x values are bigger than 4. Excuse me, on the right-hand side of our vertical asymptote. So we do want to choose some more x values. Not x equals 4, because we have an asymptote there. It's undefined there. That's part of our excluded from our domain. So maybe how about x equals 5 and 6 and 7? I'm going to go back to my calculator because I still have that function in there, and I can just go ahead and enter 5 and 6 and 7. So nice and handy. So 3 halves, and 1. So when x equals 5, y equals 3. When x equals 6, we have 3 halves, or maybe easier to think of that as 1.5 when you're graphing. And when x equals 7, y is equal to 1. So let's plot those points. 5, 3 would be here. 6, 1.5, and 7, 1. Again, connect those with a smooth curve, and then continue toward your asymptotes. And there is the graph of our rational function. We get to do another one. Here's another rational function. So I'm going to go through that same set of questions. I'm going to ask myself, does this rational function have any holes? Well, I don't think so, but maybe we should factor it just to double check. 2x squared. On the bottom, we do have the difference of squares, so we can factor that. But when I factor it out, I can see there's nothing that cancels. So no, we don't have any holes here. Intercepts. Intercepts happen when, for our y-intercepts, when x is 0. So 2 times 0 squared over 0 minus 2, which is negative 2, and 0 plus 2, which is positive 2. But it doesn't matter because up top, 2 times 0 is 0. I get 0 over negative 4. Not undefined. It's only undefined if we get the 0 at the bottom. This is equal to 0. So we have a y-intercept of 0, 0. For our x-intercept, we set our function equal to 0. Multiply both sides by x squared minus 4. On the left, that leaves us with 0 equals 2x squared. Divide by 2. Take the square root, and we get x equals 0. So look at that. That is also our x-intercept. Yes, 0, 0 is both an x-intercept and a y-intercept. Next up, let's look for those asymptotes. Vertical asymptotes happen where our denominator is 0. I already factored it up there, so I'm going to write it factored because that's how we're going to have to solve it. Our denominator is 0 here. So either x minus 2 is 0, which gives us a vertical asymptote at 2, or x plus 2 is 0, which gives us a vertical asymptote at negative 2. Horizontal and oblique asymptotes occur, well, to decide where they occur, we have to look at the degree of our numerator and the degree of our denominator. Again, might be a little easier to look in our factored form, in our unfactored form, our original form. Notice we have an x squared on the top and an x squared on the bottom. That means the degree of our numerator is 2. The degree of our denominator is also 2. When these two match, we do have a horizontal asymptote, and to decide where it is, you look at the coefficient of each of those leading terms. So on top, in front of my x squared, I have a 2. On the bottom, in front of my x squared, I have a 1. So that means we have a horizontal asymptote at y equals 2. So let's start sketching. What do we have here? So we have vertical asymptotes at positive 2 and negative 2. Oops, sorry, come back. There we go. Positive 2 and negative 2. We have a horizontal asymptote at positive 2. Okay, then we have, the only other point we have is we have that little x-intercept right there and y-intercept at 0, 0. So again, we are definitely going to need a t-table with some more points in it in order to figure out how to plot the rest of our graph. When choosing x values, I like to use those vertical asymptotes as guides, and that splits our x-axis up into a few separate areas. So first, I'm going to choose some x values over here on the left. That means I need x values smaller than negative 2. How about negative 3, negative 4, and negative 5? Again, this would be a great place to use that table button on our calculator. Oh, where was our function? There it is. There we go, 2x squared on the top and x squared minus 4 on the bottom. Enter, enter. Okay, plug in some values. I said I wanted to try negative 3 and negative 4 and negative 5. Those gave me a bunch of fractions, which can be tricky to graph. So what I recommend is arrow over to that value 18 over 5, if you hit this double triangle down here by the enter, it tells you what the decimal equivalent is. So when x equals -3, y is 3.6. I just think those decimals are much easier to graph than those fractions. When x equals -4, y is -2.6666667. Round to one decimal place. We can't graph anything more specific than that anyway, so that is 2.7. And when x is -5, we get another fraction. The decimal equivalent is about 2.4. Again, I'm just going to round that to one decimal place. So let's plot those points and see what's going on here. So when x is -3, y is 123.6, just a little bit more than 3.5. When it's -4, we're at 2.7. And -5, 2.4. Yeah, those points are going to be close together. Just give it your best shot. Connect them with a smooth curve and then continue toward your asymptotes. There's the first part of our graph. Now I want to look for some x values in between here, in between these two vertical asymptotes. I already have one at x equals 0. Okay, so I don't need to do that. How about -1 and +1? Those are the other two whole numbers in there. Let's go back to our table again, just because we have it already typed in here. -1 and +1. We get -2/3 for each. Oops, I wrote my one in the wrong place, right? Here. So -0.7 if we round to one decimal place. So -1, -0.7, +1, -0.7. So what we get going on in here is kind of a little mini parabola inside those asymptotes. And then finally, we need some x values over here because we need to see what's going on this side of the graph. So how about +3, 4, and 5? Plug those into our calculator again. 3, 4, and 5. And look at that, we got the exact same values that we did for -3 and -4 and -5. So we can just copy those down. So that was 3.6, 2.7, and 2.4. It's because of those x squareds in our function that gets rid of the negative. So that's how we ended up with those same values. Okay, let's plot the rest. +3, 3.6, +4, 2.7, +5, 2.4. Connect those with a nice smooth curve. And there we go. There's our graph. Okay, number 8, now we get into some of our exponential functions. So here we have an equation with exponential functions. We can't solve when variables are trapped up there in those exponents, so we have a couple different techniques we can try. The first thing I want to look at here, the easiest way to solve these is if we can rewrite them to have a matching base. Can we write 64 and 16 in some kind of matching base so we can use our one-to-one property? And maybe you're not sure. So guess what? Do a little trial and error with your calculator. So 16 and 4, well, I know 16 is 4 squared, right? 4 to the second power gives me 16. Can I write 64 as a power of 4? What is 4 cubed? Oh, look at that. It is 64. So just try some and see what works. So that means I'm going to rewrite this. 64 is the equivalent of 4 cubed, but 64 has an exponent on it, so I need to keep that exponent, 3x plus 2. And 16 is equivalent to 4 squared, but the 16 has an exponent on it, so I need to keep that also, x minus 1. The reason this is a good step is because now that we have these matching bases, we can just set the exponents equal to each other because exponential functions are one-to-one functions. So what we really need to solve, think about it this way, 4 to some power has to equal 4 to some power, so those powers have to be equal to each other. So that's not a bad equation at all. We'll distribute on both sides. Gather up our like terms. So I'm going to subtract that 2x. And I'm going to subtract that 6. I get 7x equals -8. Divide both sides by 7. I get x equals -8/7. Okay, look for matching bases before you try anything else fancy. Next up, how much money should be invested today in order to have $10,000 in 20 years if the rate is 4.5% interest compounded monthly? We have two different formulas that deal with compound interest. One is compounded periodically and one is compounded continuously. This is compounded monthly. So the formula we want to use here looks like this. If it was compounded continuously, we'd use the one with the E in it instead. The next thing you want to think about is, what are they asking you to find? Are they asking you to find the starting value, P, or are they asking you to find the ending value, A? So we do want to read carefully here. This says right here, how much should be invested today? That means we are solving for P. We want to plug in the values in the rest of the function, or of the formula, in order to have $10,000 in 20 years. So there is our ending balance. That goes in place of A. R is our interest rate, 4.5%. We want to change that into its decimal form. N stands for the number of compounding periods in a year. If your interest is compounded monthly, that would be 12 times a year, so N is 12. Our exponent is then that same value, 12, times T, which is time, in this case, 20. So some students like to do the math here. You plug this into your calculator and get a value. If you do that first, you do have to be careful that you don't round. You want to keep a lot of decimal places until your final answer, so you don't have a rounding error. What I like to do is just go ahead and divide both sides by this whole big expression, because our calculators can handle that multi-view calculator. So on the right, those two cancel each other and we have solved for P. On the left, this is what gets plugged into your calculator. So let's take a look at that. So 10,000 on top. Then we need parentheses, 1 plus 0.045 divided by 12, or you could use the fraction button again in there, but that's just a division. You can write it as a division or as a fraction. And that whole thing is raised to the power of 12 times 20. Enter, and there is our answer. We need to start with $4,072.55 if we want to end up with $10,000 in 20 years. So P, our starting value, our principal, was $4,072.55. Double check. Did I write that down right? Yes, good. There we go. Make sure you're using the right formula. Make sure you're putting your numbers in the correct locations. Next up, sketch the graph and dash in any asymptotes. We do need to remember that exponential functions, which is what we have here, do have asymptotes. The parent function of this one would be e to the x. That's our natural exponential function. Plus 3 means it has been shifted 3 units to the left, and plus 1 means it has shifted 1 unit up. So it is helpful, if you remember, I'm just going to try to kind of sketch it in here lightly, that the parent function has an asymptote at 0. It has an intercept, a y-intercept of 1, and it is increasing. This is a rough sketch. That's not exactly what it looks like, but that gives us an idea. So when we shift it up 1, that means the graph that we want to draw is going to have a horizontal asymptote at 1. And then maybe we find some points to see exactly what's going on. That original y-intercept at 0, 1 is going to go to the left 3 and up 1. So since it moved to the left 3, I'm going to try -3 here as my first x value. Maybe I want one smaller than that and one bigger than that, and maybe another one just for good measure. Let's see what we get. I'm going to use that table button again because it's so fun. So this time we have e to the x plus 3 is the exponent. Then we arrow out of the exponent and we have that plus 1 for our vertical shift up by 1. And the values I want to put in are -3 and -4 and -2. Okay, again, round to 1 decimal place. We can't graph anything more specific than that. So for x equals -3, we get a y value of 2. For x equals -4, we get a y value of 1.4 if we round that. And for x equals -2, 3.7. And maybe just for good measure, I'll do one more point. Let's do -1, 8.4. So plot those points. I'm going to erase this original parent function. We were just kind of looking at that. Okay, so -3, +2 here. -4, 1.4 would be about there. -2, 1, 2, 3.7. And -1, 8, 5.4. So that gives us our nice, smooth exponential curve shifted to the left and up.